bright and some stars are dim. Have you ever noticed that?
Yeah.
So a guy named Hipparchus.
Are we going out soon? He told us to remind you.
As soon as the moon's not out, which we got another week.
Yeah, it's in big area.
Said remind you.
So this guy named Hipparchus was a Greek who decided he would classify the stars based on their brightness. And he called this the apparent magnitude of the star. That means how bright it looks to us. And the brightest star he saw, he called apparent magnitude 0. And the dimmest star he saw, he called apparent magnitude 6. And he would just take a star that he sees, like Alpha Centauri, and that's pretty bright. And Polaris, that's the North Star. I'll show you that when we go out there. That's not as bright. It's a 2.5. And the naked eye limit is 6. That's the dimmest star you could see. So the numbers go up for how dim they are. Of course, with the binoculars, you can see way dimmer stars. You can see all the way up to a 10. And with a telescope, a 1-meter telescope, that's a pretty big scope, you can see almost 20 apparent magnitude. The Hubble and Keck can see 30 apparent magnitude. That's a really dim star, the Hubble telescope can see. You see what I'm saying? What?
Where's the Hubble located?
In space. It's orbiting the Earth.
So,
Yes.
so a 30 could be very bright, just very far away.
Yes. If it's very far away, it'll look dim to us. So this is apparent magnitude. Good thinking. You're skipping ahead. That's my next slide.
Sweet.
Now, if you go towards the negatives, that's something that's real bright to us. So the full moon is real bright. It's a negative 12.5. The sun is way brighter than the full moon. It's a negative 26.7 using this scale. So Hipparchus started the scale, and that scale has been widened since Hipparchus, since they've invented telescopes. Yeah?
What's Sirius?
Sirius is the brightest star in the sky. And for some reason, Hipparchus didn't rate that one. But that's the dog star. It's because it's in the constellation Canis. And it's a negative 1.5. So that's the brightest star in our sky, Sirius. I'll point out Sirius next time we go out there. Are you serious?
Are you serious? Do
Is
you
that the North Star?
No, the North Star is Polaris.
Did they name Siri after that?
It is in the Big Dipper.
Hmm?
Siri?
Yeah.
She may have been named after that. So if you look at the Canis constellation, here it is. Looks like a dog in the sky, and there's Sirius. Now, I bring this, can you tell it's a dog? That's the head, and there's the tail, and there's the legs. They thought there was a dog running around in the sky. It wasn't, it's just a bunch of stars. Now, take a look at Sirius. Sirius is a lot brighter than Mersenne to us. But if you were to put Sirius in Marsan, did I say Mersenne? Yeah, that should be Marsan. I don't know which one of these is wrong. It's either Mersenne or Marsan. If you put Sirius next to Marsan, Marsan is actually brighter. But they aren't next to one another in space. Sirius is a lot closer to us than Marsan. So somebody else came up with a scale of what's called absolute magnitude. Absolute magnitude is how bright the star actually is if you were to put it out in a point of space 10 parsecs away. So it's an equal comparison. For instance, what's the brightest star to us? It's the sun. Why is it so bright? Because it's so close. But if you put the sun at 10 parsecs away compared to other stars, our sun would actually be a pretty dim star. Our sun's pretty dim compared to other stars. It's bright to us because it's so close. So our sun has a very high apparent magnitude, It's obviously very low, very negative apparent magnitude because it's so close to us. But in actuality, if it were 10 parsecs away, it would be dim, like a lot of other stars are. So that's the difference between apparent magnitude and absolute magnitude. Absolute magnitude is a measure of the brightness if you were to put it 10 parsecs away, which is 33 light years, which is kind of a normal distance in space. Not too close, not too far, just out there somewhere. You see what I'm saying?
So how far did you say a parsec was again?
3.3 light years. 10 parsecs is 33 light years. And if you did that, Marsam would be brighter than Sirius. But Sirius is brighter than Marsam because Sirius is only 2 parsecs away, and Marsam is like 10 parsecs away. So Sirius looks way brighter to us. What's that?
It's essentially like a dog constellation.
Yeah, that's Canis.
Yeah, I can see it now.
You can see it? Yeah, that's Canis. Have you ever looked at the stars and noticed that they come in different colors? You can classify stars by their colors. And we learned in an earlier chapter that the reason why something is a certain color is because of its temperature. Do y'all remember that? Blue is a hot temperature. What's the coolest temperature? Red is the coolest temperature. And there are all sorts of in between. And if you have about equal amounts of all colors, you'll look white. So the blues are the hottest and the reds are the coldest, and the white's kind of in the middle. And they came up with a way to classify stars by their temperature. And the hottest stars, the bluest stars, are called type O stars. And the coolest stars, the red stars, are type M stars. And there's all these letters in between. It'd be nice if they just went A, B, C, D, E, F, G, right? But they don't. They go way out of order. Santana, you with me? And the reason why is because they're taking an old version of type A was the first one, not the first one to be discovered, but they're using a different way of classification and making it based on colors instead of what it was originally based on. So type O stars are the hottest stars, and they're blue, and it goes O, B, A, F, G, K, M. And you have to memorize that order, but do you want me to give you a real easy way of memorizing that order?
Yes.
Yeah, let's say it.
There's an acronym.
What is it?
O, B, a fine girl, kiss me. That's what I ask with my dates. Oh, be a fine girl, kiss me. Or girls, you can say guy if you want. Oh, be a fine guy, kiss me. And or guys, you can say that if you want. Whatever. We're not going to hate here. Oh, be a fine girl, kiss me. Oh, be a fine guy, kiss me. That's the order from hot to cold of the stars. You can see the temperatures here. This is the surface temperature of the star going down.
So O is blue. Okay.
O is blue, it's the hottest. M is red, it's the coolest. Yes?
Is there any relation of this chart to that the bend in the, I forget what it's called, but where all the colors were, where it bends, and that's where like the light you can. I forget what it's called.
Oh yeah. Well, blue bends easier than red.
It wasn't that. It was like
That
an
has to do with
earlier
wavelength.
chapter where there was all the different lines.
Yeah, you're talking about the black body curve.
Yeah, the black body curve.
Yeah, same thing. The black body curve goes through a rainbow, and the visible spectrum is somewhere here. Red, orange, yellow, green, blue, indigo, violet. if the star had this radiation coming out of it, it would be blue because it's got more blue than red. You remember that?
Uh-huh. So, are there stars that aren't visible to us?
Yes. We're going to get to that in just a second. But if a star were so cool that it dropped before that, then you wouldn't be able to see it.
Right.
But that's a star that's not doing any fusion. We call those failed stars. Because there's no fusion going on in the center and they're kind of cold. We'll talk about those in a minute too. Stars come in different sizes. There are big stars and there are small stars. There's our sun. Our sun is bigger than that little tiny red dwarf. But we're smaller than Sirius.
Jeez.
But if you look at Sirius compared to Arcturus, look how small Sirius is to Arcturus.
Oh
my
well.
gosh.
Look how small.
And Aldebaran, way bigger than Sirius, and look we're smaller than Sirius.
Oh my god.
And then if you take Aldebaran and you make it real small, look how big Antares is to Aldebaran.
Wow.
Oh my
And there's
god.
Betelgeuse. That's the biggest one that's in Betelgeuse is the largest one in Orion. The big red ones. But Betelgeuse is even smaller than these. So here's a video showing you all of these things.
So
It's a great video.
they have planets
Yeah,
rotating.
very likely have planets. They all do.
Looks pretty sure it's like Earth.
But they're so far away you can't see them.
That was like
intense.
really kind of scary.
I told you that was intense.
Dude.
I don't know what
I'm like scared.
The star can get pretty big. But don't feel sorry for our sun. Because in 5 billion years, it's going to start to expand and grow. And it's going to be real big like these.
Then we're done?
Yeah.
Oh yeah, we'll probably be done at that point. Unless we can move the Earth.
Go to the next one. Just push it
Yes.
somewhere else.
Our closest star is the Centauri one, right?
Alpha Centauri. Mhm.
So if that star were to blow up, would it affect Earth at all?
Too far away.
Too far.
Yeah.
Do we need to know the classification table? Like the temperature range and the sample star? Or do we just need to know the O, B, A, F, G,
Yeah, that's all you need to
and
know.
then the colors?
Yeah, O be a fine girl, kiss me. If you just know that, you'll get the test questions right.
Alright.
Okay. O being blue,
Blue, white.
M being red. Oh, and by the way, you probably should know this. The sun is a whoops. The sun is a G.
So the yellow.
Yeah, the sun is a G. We're yellow.
The yellow.
And it's interesting. Each classification, they actually have numbers that go from 1 through 10, or from 0 through 9. So a G0 is the hottest yellow. A G1 next, G2, G3, G4, G5, G6, G7, G8, G9, K0, K1, K2, K3. So there's 0 through 9 numbers also. So the sun is actually a G2. That's a nice little bit of trivia to know. The sun is a G2. And so I always remember Gatorade 2. Remember when they came up with that? I was real happy about that. Because that's our sun.
Actually, the best.
G2.
You think there's any relation there?
I was just like, hey, G2, that's our sun. And it's now a drink. That's neat. It's two things. So they came up with this diagram. A couple of scientists named Hertzsprung and Russell. And this is a Hertzsprung-Russell diagram. And what they do is they chart the luminosity on one axis. That's how bright the star is. Not how bright we see it, how bright it actually is. How bright the star actually is the luminosity. And the temperature of the star is on the bottom. O, B, A, fine girl, kiss me. Coldest stars on the right, hottest stars on the left.
Why don't you just say, oh boy, a fine girl kissed me?
Oh boy, a fine girl kissed me. I like that. We can say that. I'm not anti-saying that. So, the brightness on this side, the temperature on this side. And they found if you take each star and you plot it on this graph that there's a pattern. That's the coolest thing about this. There's a pattern. Almost all stars lie within this line here, which we call the main sequence. Can you say main sequence?
Main sequence.
Most stars lie along this. And what does that mean? That means if they're hotter, if they're O-type stars, they're usually brighter, very high brightness. If they're cooler, if they're M-type stars, cooler is down here. If they're cooler, they're usually not as bright. Does that make sense? So we have what's called this main sequence of stars. Hot ones that are really bright, cool ones that are pretty dim. And what scientists have figured out is that stars will remain on the main sequence for most of their lives. Let's find our sun. It's a G-type star, so it's right in here.
It's very deep.
And it's got a luminosity of 1 solar unit. We measure luminosity based on how bright it is compared to our sun. So if you just follow the 1 across, there's our sun. It's a G, and it has 1 solar luminosity, so there it is. So everything up here is brighter than our sun and hotter than our sun. Everything up here is brighter than our sun, but cooler than our sun. And everything down here is bright, is dimmer than our sun, but hotter than our sun. We call those the white dwarfs. They're dimmer than our sun, but hotter than our sun. We call these the red giants. They're brighter than our sun, but cooler than our sun. And we call these the blue giants. They're brighter than our sun and hotter than our sun. So there's kind of different locations along this, we call it the HR diagram. On this HR diagram, there's different locations for different types of stars. And what you're going to learn is that stars have a lifetime to them. Stars are born, they live for a long time, and then they die. Just like people do. So, here's what the stars do. The stars are born and they come into the main sequence when they're very young from this direction. In other words, a star starts as a big nebula, and then that nebula collapses into a star. And it comes in this direction, meaning that for a while, the nebula is cooler than our sun, and it's brighter than our sun. You can actually see the nebula glowing while it's becoming a protostar to form the sun. So, stars enter the main sequence from the right, and then they burn on the main sequence for a lot of years. The sun will burn for 5 billion years at this temperature and this luminosity. And then the sun will start to die. And when it starts dying, it creeps off the main sequence and goes this way. It gets bigger, it gets cooler, and it forms a giant. And it's brighter. It's actually, our star will be brighter when it's a giant. You know why our star will be brighter when it's a giant?
Be bigger.
Because it's so big.
There's more mass.
It grows bigger. It's like having a light bulb that's bigger. That's going to be brighter. You see what I'm saying? The bigger the light bulb, the brighter it is. So when our sun dies, it's going to start growing, and it's going to start cooling off. It's going to go from yellow to red. But it's going to be brighter. You'll be able to see it from a longer distance away. And so when stars die, they take off the main sequence and go this way. These stars up here go to the right, this way. And here's the giant phase. These are dying stars. And then what's real cool is all of a sudden when the star dies, it goes boop. It like jumps way across here and becomes a white dwarf after the star dies. So we have this kind of sequence where it comes in like this, it's born, it lives on the main sequence, then it dies, becomes giant, and then it pops over here and lives as a white dwarf for these are the very old ones. The ancients. You can think of an actual white dwarf, like you might see on The Hobbit or something like that. They're old and they have white beards, and they're old. That's what the white dwarfs are. They're already dead stars. We're going to learn about those next. Yeah.
So when you get to the white dwarf stage, you're just like a ball of helium?
You're a ball of carbon. A giant white diamond floating in space. We learn about those tomorrow.
Okay.
They're exciting.
So the helium turns to carbon?
The helium and hydrogen all fly off into space, and you're left with the carbon that's in the middle. That was formed from the helium and hydrogen doing fusion. We're going to learn about that tomorrow.
Okay.
Can you wait till tomorrow?
I can.
It's exciting. Do y'all want to see Hertzsprung-Russell diagram video?
Would any of those stars have a liquid core? Or like all of them just...
No. It's a solid core when it reaches a white dwarf.
They're diamonds?
I think we have to go for a while.
Yes, Marine Bio can go eat lunch, but the rest of you stay and watch this video.
Wait, no, wait.
No?
No, please.
I got a couple videos. And one more thing to talk about. Watch this. This is cool. They're sorting stars by brightness and color.
This is a Hubble Space Telescope image of the crowded core of the globular cluster Omega Centauri. The brilliant colors of the stars are real. They correspond to stellar temperatures. They can also be used to trace stellar evolution. Astronomers like to know how blue the blue stars are and how red the red stars are. So we'll first sort these stars out by color, blue on the left and red on the right. Next, we'll sort the stars according to brightness. The brightest stars at the top and the faint stars at the bottom. The final plot you see represents different stages of evolution of stars. Stars spend most of their lifetime burning on the main sequence. When the fuel starts to run out, they expand to become red giants. They find a new source of fuel, helium, and burn blue hot. But even that runs out. They end up burning out as white dwarfs. Based on images for the Hubble Space Telescope, we've assembled a true plot that is a snapshot of the life history of stars in this ancient cluster.
How cool is that?
Pretty cool.
That's cool.
Let me back this up
Yeah, what do you think?
one more time.
The crowded core of the globular cluster
Watch how they
Omega
separate.
Centauri. The brilliant colors of the stars are real. They correspond to stellar temperatures. They can also be used to trace stellar evolution. Astronomers like to know how blue the blue stars are and how red the red stars are. So we'll first sort the stars out by color, blue on the left and red on the right. Next, we'll sort the stars according to brightness. The brightest stars at the top and the faint stars at the bottom. The final plot you see represents different stages of evolution of stars. Stars spend most of their lifetime burning on the main sequence. When the fuel starts to run out, they expand to become red giants. They find it...
Isn't that cool?
She's a lot happier during basketball. No, I'm just kidding.
Hey, that is it. That's all I've got. Read the section, chapter 35, and go eat lunch.